or to cause Creutzfeldt-Jakob, which is disease in youth. So even though it shouldn't be in there, ideally, they still try to prevent it from happening as much as possible. So factors determining adverse effects, so these are again the basics of toxicology. First of all is the intrinsic toxicity. Some things are simply very poisonous, more toxic than other things. For instance, water is less toxic than, well, whatever that guy from Russia got in England last week. Then there's the dose. If you drink or eat something more, then you get more severe effects than if you drink less of it. Then we have the exposure conditions. Of course, there's drinking, there's eating, but you can also get a toxic dose via inhalation, so then it goes via the lungs. You can also get it through the skin. So there's various ways of how you can get sick. And then there's, of course, there's the response of the host, which depends on the species, the age, the gender. So all of these things determine how much is enough to cause an effect in you. If you weigh more, then you need a higher dose than someone who weighs less. Then, as far as food safety risks, so first I want to go into what is a risk in general and hazards, and then I will apply it to the insect specifically. So a risk, this is a legal term, well it's also a risk management term, but that's where it originated, but currently this is the legal definition in the EU. So a function of the probability of an adverse health effect and the severity of that effect consequential to a hazard. So there's a lot of words in here that may mean something to you, but they mean a very specific thing in legislation. So what it comes down to is that the risk is a probability times the severity. It's a bit difficult to understand conceptually, so that's why I have here a table. And it's really quite simple to get it. Let's say you have something that is almost impossible to happen, but it's catastrophic if it happens. Let's say a nuclear disaster. Then it would have a score of 5. If something is very likely to happen, but it does some damage, then it's 10. Now, if it is here, so it is catastrophic, and it's very likely, probably shouldn't be doing it in the first place. The point of this is that you cannot prevent everything. The idea is that you try to prevent things where it happens. So, for instance, if you have bacteria in something, then as soon as you heat the product, the bacteria are out, and then it doesn't matter anymore. So then the heating step is what determines whether or not it's safe afterwards. So it's about prioritization of measures to reduce the risk, so that you go from here to here or here. Ideally speaking, this, avoid, don't do it. This, try to bring it down, and here, well, also try to bring it down here. It's, well, really not that important, even though you should, of course, still take it into account. Let me give an example. If there's pieces of plastic in a Mars bar, which happened a couple of years ago, you know, it's very unlikely to happen because of all the measures that they have. A piece of plastic in your Mars bar, you're not going to die from it. So the damage is very, very low. But if you look at the damages with regards to the reputation of Mars, how much they have spent on recalling all of their products, it can still be expensive. So just because it's over here doesn't mean that you shouldn't do anything about it. But of course you should do more about these things. Generally speaking, food safety hazards. So let me go back to the definition real quick. So consequential to a hazard. So the hazard is defined as an agent that causes something, a toxic effect. So it's the thing that causes you to get it. So usually we have 4 categories of hazards. We have chemical, biological, physical, and allergens. Sometimes they are shared under the chemical, sometimes the radioactive effects are taken separately, but usually these are the four categories that we use. Biological, some bacteria, some fungi, they can also produce toxins, and then the toxins are under here. So if there's mold on your bread, you're not going to die from the mold, you're going to get cancer from the aflatoxins that are produced by the fungi. Then the insect safety with regards to the hazards specifically for insects. Now an important thing to know here, and that is something that has been touched upon by many before me already, is that it's very specific which insect that you produce, whether or not it, in which way it is hazardous. For instance, there are some insects that produce toxins themselves as a defensive mechanism. Probably shouldn't eat those, at least not in the way that when they produce that toxin. For instance, if it produces toxin in a fetal state, well, as long as you eat it as a larvae, no problem. So that's an important thing to know, that it depends on the specific insect. And a little bit of background about that. A lot of research has been done on being able, on various wild insects. So they catch them in the wild and then they eat them. The thing is that they are very different species than what is generally produced as indicated by the other presenters already. So the species that we produce currently in Europe are very different than what the research has been done on. So now we have to catch up on all these other species with regards to the research that we do. So first of all, I will go over the chemical hazards relevant for insects. The main issue with insects, with chemical hazards, is the accumulation, so the repeated doses, and that they store it in their body, or the excretion of substances in insects from these substrates. So they eat something, and apparently there's too much of something in that substrate, and then they store it in their body. For instance, if they store mercury, if there's too much mercury in the substrate, they eat the substrate and they will store all of the mercury, then of course the insects also become hazardous. Just an example. And of course, as a farmer, you want them to not be affected by whatever is in the substrate, so increased mortality and decreased growth rate among insects are also important factors to take into consideration. If they don't store it, but they still die from it, then, well, you don't have any insects. So those are the basic principles of accumulation and increased and decreased growth rate. So these are the two main issues with all of the chemical issues, basically. So there's a couple of chemical hazards. Mycotoxins. These are fungal toxins, so these are toxins produced by fungi, molds, stuff like that. And they're usually very highly resistant to heat. So even though you heat it, they're not going to be removed. If it's in there, you cannot get rid of it. Then there's the metals, speaks for itself. You can do something with high mercury or lead in it. Environmental contaminants, so these are contaminants that come from the environment. In the 70s, for instance, it was common that there was lead in gasoline. All this lead has bled into the environment, and it's still, well, used to be found in agricultural products as well. And then there are pesticides. Of course, you shouldn't use too much of them because they are basically neurotoxins. They're designed to kill insects or whatever other species that you, or whatever other things you can think of. Probably shouldn't be them. So that's why legal limits for most of these things have been established. These are called maximum residue limits, levels, and have been set for most chemical hazards. As long as the level of that chemical is below that threshold, you can still market it. If it's above, no. So you should use as little, and you should try to prevent these things from occurring in your products. The chemicals of concern for insects, and this is something that I mentioned earlier, it's very specific on the type of species that you grow. For instance, for black soldier fly, they accumulate cadmium, which is a metal, Not so much the case for the yellow mealworm, for instance. Arsenic, again, is a problem for yellow mealworm, not so much for black soldier fly. So if there's too much arsenic, you can give it to a black soldier fly. If there's too much cadmium, you could give it to a yellow mealworm. Sort of. They both have a high tolerance as far as growth rate and mortality, so they're really quite resistant to aflatoxin B1, which is one of the mycotoxins, the fungal toxins that I talked about earlier. And is not retained, so they don't store this particular mycotoxin. And then there was some research on bioaccumulation of antibiotics, anti-epileptic drugs, so basically veterinary drugs that they give to other animals to be able to, and they also gave them fungicides, so pesticides against fungi. They gave them insecticides, probably not so much. Now to go over biological hazards, so these are the things that live, because if it produces something, then it goes into the chemical category. So there's a couple of pathogens that you have to take into account when you produce insects. First of all, pathogens. Pathogens are the name of biological hazards. For humans, if it's hazardous to humans, then yeah, you should do something about it, especially if you're trying to feed them to humans. Then of course you have to take into account the target animal species. If you feed an insect with something that has an animal pathogen, for instance something that makes a chicken sick, then you feed the insect to the chicken and all the chickens in your farm get sick. Not a good idea. And then of course you have to take into account the insect species themselves. If you feed them with something that has a pathogen for insects in it, then there will also, the whole colony, your whole farm as an insect farmer will collapse. And it's something important to notice that mammal pathogens, so mammals, humans, etc., are usually not the same as insect pathogens because of a very different structure. If it makes an insect sick, it probably doesn't make a human sick because it's a very different, very different species. Something to know is that, again, insects can transmit pathogens from the substrate to, the target species and from there to humans. So, for instance, you have salmonella on the substrate. Then it will not grow on the insect, but the insect will transmit it to the poultry if the poultry eats it. And then all the poultry in the farm gets salmonella, and then the human gets the salmonella. Of course, it's something that you want to prevent. And substrates, they can contain insect pathogens and insecticides, like I mentioned before. I will skip the physical hazards because it really depends on how you eat it. If you grind it into a powder, then there will not be any physical hazards left. Physical hazards are, for instance, pieces of glass, pieces of plastic. I mean, you can choke on a wing from an insect or a leg or something, but for this it's not so relevant. So I will go over allergens directly. Two main issues. First of all, the food allergens. Some people may be allergic to nuts, some may be allergic to crustacea. And indeed, just like crustacea, insects can also contain certain allergens. And so if you are allergic to house dust mite or crustacea, then it's very likely that you might also be allergic to the yellow mealworm. And secondly, worker safety. Earlier in the presentation of Ferdinand Balagino, you saw him wearing a face mask. Probably he wore it to avoid contaminating the insects themselves, but probably he also wore it to avoid getting allergic to the chitin. What happens is that these small particles are related to lung disease. And some people have actually gotten allergic to insects by being near insects and inhaling these particles, even though they don't eat So the chitin is the main component of the insect's exoskeleton. What they wear. So chitin, what is chitin? There's chitin in butterflies, there's chitin in fungi, in mushrooms, in of course varying amounts. And a lot of insects, crustacea, you see a lobster. So what it is that it's basically this structure. So it's very, if you're knowledgeable about natural science, these are they look very similar to mussels. So what happens is that you have these, the large particles. If you inhale those, well, nothing really happens because they're too large to do anything with. Then there are the intermediate, which is size, and they will activate the human immune system, and people will get an allergic reaction to this. Here under you see the source of this. And what happens is that humans and other mammals, they break down these larger particles into smaller particles. So the intermediate chitin, so the relatively big, medium-sized particles, they cause an allergic effect. And then the human body, via enzymes, they break it down into smaller particles, and as soon as these smaller particles are achieved, then it will activate a different mechanism that stops the allergic reaction. So the point is that if you give someone particles of this size, they will get an allergic reaction. However, if you give someone particles of this size, it stops an allergic reaction. And it is hypothesized that this could mean that if someone is having allergic reaction to a different allergen, you give them these particles so that they stop being allergic. And finally, I will give an example of a research project that I've been involved with myself. I'm not on the author list because I'm always only involved in the data research. So tolerance and excretion of the mycotoxins, so these are the fungal toxins, well, I'm not giving names, from contaminated substrate in 2 species. So to summarize the methodology, first of all. So the thing is that in a laboratory we try to be able to replicate things. So if we give them the insects, for instance, corn with these mycotoxins, then we don't know the levels exactly and it's very difficult to replicate. So what we do is we take safe feed, so safe substrate, and we spike it, so we put a little vial of mycotoxins on it. So we know exactly how much is in there. And they were analyzed to check whether they accumulated these mycotoxins. So what we used the lesser mealworm, discussed in depth earlier, the physiology earlier, black soldier fly. And this is what they look like. One of three, by the way. So mycotoxins, first a little bit about those. These are fungal toxins, as I mentioned earlier. An example is aflatoxin. What does aflatoxin do? Well, it's found in many staple foods, for instance, corn, rice, spices, etc. Particularly a very big problem in Africa, because the levels there are much higher, and the effects are it stunts growth, it leads to liver disease, and because the doses are much higher there, even very young children get to have a problem with that. Another problem is that it is transferred from the feed to food. So for instance, if a cow eats corn with a lot of mycotoxins in it, then the milk will also have mycotoxins. Well, not those, but a different metabolite. They will also have mycotoxins in them. So even those types of foods are also dangerous. And like I said, the health effects mostly affecting the liver in cancer. So what we did is, first of all, we had some safe food, clean feed, and we spiked it with a little bit of these 4 aflatoxins. Well, we had the black soldier fly, we had the yellow mealworm, the lesser mealworm, and we fed them, well, in this case with water, and for the mealworm with an apple as well. For 14 days, and then we separated the rest of the feed from the insects. and then we transfer them to clean feed, and then for another 2 days we let them starve, and then we separated the residual material after cleaning the cuts, after they were starved. So all these different parts, basically the feed that we gave them, the insects themselves, the excreta, everything we analyzed for where these things were. So these were the mycotoxins that we used, plus the main metabolites. So you have, for instance, you have here aflatoxin B1. That's the main molecular structure, but you also have different molecular structures that are more or less toxic. Yeah, so these things, and we also analyzed a couple of those. So the main metabolites we tested. And we had the insect, leftover feed, frass, etc. We use them at 1, 10, and 25 times the maximum residue levels. So if it's at this level, it's still allowed. If it's at this level, not really. And if it's at this level, not really, not at all. So these are the levels that we use to feed them, because if you feed them with something like this and they don't accumulate it, then, well, apparently you can feed them with something that is not fit for other animals. So the results are both species, as far as growth rate and mortality, they can tolerate these mycotoxins no problem. So they are largely unaffected by these, even if it's very high, any other animals would have health effects. No problem for these species. And the insects excreted or metabolized mycotoxins in their feed. The problem is that, so we checked, basically we measured how much did we put in, and then we measured how much did we get out. The feed, the excreta, and the insects themselves. Logically speaking, these two should be equal, because what you put in should also come out, because where else is it supposed to go? That didn't happen. There was a discrepancy between the levels that we fed them with and the levels that we got out. So what happened to those things, we don't know. So this suggests that the mycotoxins were metabolized into other substances. We only measured the main metabolites. So maybe they were turned into different metabolites, different chemical structures, which are also toxic. Then we still have a problem. Maybe they are less toxic, still good, but if it's a different one that's more toxic, we don't know. But you can speculate, of course. Maybe insects can neutralize these mycotoxins. So if you feed them first with these feed that you cannot do anything with because it's not allowed to be fed with conventional livestock, at least you can feed it to the insects first, and then you feed the insects to the poultry, and then you can still use this feed, which is cannot be used for other animals. And that was the end. Thank you very much for your attention.